Hi, welcome to Ethereal University, Department of Electrical Engineering, course EE301, Crystals. This is video part 1. In this video, we're going to talk about ultra-high precision crystal oscillators, theory and application. This is for more advanced audiences. Okay, in this video, we're going to demonstrate theory and realization of ultra-high precision crystal oscillators at 10 parts per million tolerance or better. And we're also going to show that the existing engineering models are completely bogus and success in the field has been achieved completely by accident or by engineering fiat. And we'll show you how that could occur. And for those people who are not familiar with the term parts per million, okay, it's very similar to the concept of percent. Okay, so if you say you want 10% of something, what you were saying is you want 10 parts per cent. 10% is shorthand for 10 parts per cent. Okay, cent is the Roman numeral for 100. C is cent is 100. So what you're really saying when you say 10%, you really want 10 parts per 100. Okay, so to find 10 parts per 100 of $47.59, you take $47.59, divide by 100, and then take 10 of those parts to arrive at $4.76. Likewise, 10 parts per million is just as it says, it's 10 parts per million. Okay, and so to find 10 parts per million of a $47.59, you take $47.59, divide it into a million parts, and then take 10 of those parts. That would be 10 parts in a million. Some people say 10 parts in a million. Some people say 10 parts per million. It's the same meaning. And this, of course, would be 4.8 hundredths of a cent, or hundredths of a cent, because that would be a cent right there. Okay, and just so for compatibility, that 10 parts per million is equivalent to 0.001%. Okay, so now the question is, well, why does anybody need 10 parts per million in your crystal time reference? Because most everyday applications can get by with 1,000 parts per million, or 0.1%. And for scientific exploration, most of the discoveries for new forces or previously unknown effects are found in the margins. Let me give you an example. The precession of Mercury. Okay, Mercury's precession disagrees with Newton's law by 43 arc seconds over 100 revolutions of Mercury's orbit. 43 arc seconds over 100 orbits is 0.33 parts per million. This shows you that it doesn't take a lot of error to disprove a scientific theory, or at least to show that the theory is wrong, or that it needs to be updated or replaced, or yada, yada, yada. And again, another example is when Galileo was to prove that the Earth was not the center of the universe, he had to improve measurement precision of the planets in the night sky in order to a higher degree, in order to prove that the Earth is not the center of the universe. Okay, so very, very fine measurements are very important in the scientific realm. Yeah, for everyday access, for everyday things, we probably can get away with a lot less than 10 parts per million accuracy. Okay, and what we noticed in New Electromagnetism V5 in the experiments will run really quickly, is we noticed an anomaly at the 40 microvolt range. So basically what you are looking at is, this is the experiment. A motor moves this magnet around this loop. Okay, when the magnet is at this location here, we end up seeing a ripple in the measurement. The red is the measurement. The black is the theoretical prediction. As you can see, the red and the black agree 100% all over the place. The green and the blue are the two components of the theoretical. The green is the inertial field effect. The blue is a magnetic field effect. You combine those together to get to the black. So we're just showing you the components of the different field phenomena that's involved in this experiment. Now we know that this is not noise because it repeats when the magnet comes back around. And it goes away when the magnet's on the backside. So this measurement is taken when the magnet's here. This measurement is taken when the magnet's back here where there is no loop of wire. And then when the magnet comes back around, that's the measurement. We get the exact same repeating pattern that you see here. So because the pattern repeats, it's definitely not noise. And we run the experiment now with a complete loop. We get the anomaly on both the back side, okay, and the front side. I wish this thing would stop doing that. Okay, now people are saying, well, those little effects you're measuring are so tiny. How can 45 microvolts be of any meaningful use to humanity? Why are you chasing down these little tiny effects? Well, that's just it. Most of the little tiny effects can be scaled up through engineering. Here you're seeing an array of MOSFET transistors. They found by making this MOSFET transistor smaller and smaller and smaller that its performance became more and more ideal. But the problem being is that the transistor was so tiny you really couldn't handle much current with it. You really couldn't do much with it except as for logic in a chip. So in order to make a MOSFET transistor that you can move, you can switch off large amounts of power and high voltage and high current, they put thousands of them together in an array so that you have thousands of them working in parallel. So now you have a chip that can switch hundreds of amps at however many volts you want it to work at. This is an example of one of those devices. It's about half a centimeter on a side. And this device can switch continuously 50 amps or it can pulse up to 400 amps. And this device costs $3. If you showed this to me when I was getting into electrical engineering in the middle or the early 80s, and you said they have a device that's smaller than half of your thumbnail and they can switch 100 amp or that can pulse a 400 amps, I'd laugh at you. I really would. With very, very little resistance. The resistance of this is in the milliohms. So this is almost bordering on a short circuit. There was no device back then that could do that. Okay, and in the experiments, like the experiments I showed you with the loop of wire and the magnet, part of our error was determined to be from the crystals used on the Arduino board to drive the motors was off a significant amount. Okay, and so what we need to do is when we're taking our measurements again, we need to lock down any source of error such that any leftover amount we can attribute to new forces, because Ethereal Mechanics says there's another set of forces much smaller than the electromagnetic forces, and this may be what we're seeing. But we have to take precise measurements with all of the known errors locked down so we can separate out what's a measurement error from what is a residual that might be part of another force or another effect that was as unknown before this. Because it was so small, people might have ignored it. So the original idea, the way I was going to solve this problem, was just go buy crystal oscillators, because you can buy them already in a little tin can where somebody's already measured them, makes them perfect, and these are little oscillators are already put in a little tin can and they're already tuned to 10 parts per million. And I like the company ECS seems to make their precision is the best. I'm not going to get into all the reasons right there, but it's the one that keeps coming up when I do the search for the things that I want. So I did buy a whole bunch of these at different frequencies to have them. Okay, but the problem I'm finding is they don't make any crystal oscillators that are in the 10 parts per million tolerance that actually work at 5 volts. Okay, because we look at some of the devices we're going to be using, like the Atmega 328P. In order to get it to run at maximum speed, you've got to run this device at 4.5 volts or more. Okay, so those crystal oscillators I showed you before, they only work to 3.3 volts max. And 3.3 volts max on here is about 12 megahertz. Okay, and there's a lot of other logic devices out there, a lot of analog to digital converters that work in the hundreds of megahertz range that we're going to be looking at. And we want to be able to punch these things up into the hundreds of megahertz using phase lock loops and other devices. And a lot of these phase lock loops work best at 5 volts. Okay, now the crystal hookup for this 328P processor follows pretty much the same as all the other devices that use crystals. You have two crystal inputs, you have to put two capacitors on it, and you put your crystal across the leads. And the problem is the computation of these two capacitors was driving me up the wall. There was no clear indicator on exactly how you go about doing it. And I looked at a lot of different data sheets. These are the phase lock multipliers that I talked about. We get a whole variety of these. These can take a crystal, and using a phase lock loop, they can synthesize hundreds, up to 200 megahertz, I believe, for this guy here. I have another one I believe can go into the gigahertz range. I don't think it's that one, but I do have another one. Okay, and a lot of these require the device to work at 5 volts to get the full range out. So we're not going to be driving these from a crystal oscillator. We're going to be driving them from a crystal, because the crystals can go up to higher voltages. Okay, and one of the devices had a much more complete app note than any of the others, and they showed that their device has already built-in capacitance for you, so you may not have to add external capacitance. And then you account for the stray capacitance on the leads, and then you may have to add extra capacitance. As long as the total capacitance on either side is correct, this thing will oscillate at the right frequency. So the general consensus here, what we need to do is, and this is the Pierce oscillator, is the capacitance on either side of the crystal needs to be twice the load capacitance of the crystal. Okay, and the crystal that we are looking at has a load capacitance of 18 picofarads, which means we need to have 36 picofarads here and 36 picofarads here. Now, there is a way you can adjust these so they don't have to be the same, but you have to get into series capacitance, yada, yada, yada. But we're not going to talk about that now. Okay, so they say we have to double the load capacitance on both of these. And the thing that just bothers me the most about that is this digital logic devices here. These are designed to drive high capacitive loads, which means this guy should really be doing nothing to this entire circuit whatsoever. So I'm not sure why this one is even here. This makes absolutely no sense to me whatsoever. Also, there's no information of, well, how close do you have to be for the capacitance for it to actually work? And how is the frequency impacted if you're not perfect? I mean, what's the derating if I'm off by 2 or 3 picofarads? Is it going to matter to me in the frequency of the final result of the oscillator? There's no information like this anywhere. Okay, so I went online to Wikipedia, and I found, oh yeah, this is the tried and true effective, they're calling it the equivalent model circuit for the quartz crystal. When I went to college, the professor said, don't do any math on this thing. It's notional at best. It's not for real. But that information seems to have been lost in the transcending generation because Wikipedia went and applied the Laplace transform to model this, which makes no sense to me because crystals have a much higher Q than a single LRC circuit, and that's actually mentioned right here. So how can you use this, the model for a low Q circuit, when a crystal has got a Q about 100 times more precise? And what the Q is the selectivity of the frequency. I'm not going to get more into that. Okay, so the capacitor that we're going to be using here is we're going to be using an ECS 10 megahertz crystal, which has a load capacitance of 18 picofarads. Its tolerance is 10 parts per million. Its stability is 10 parts per million. And the temperature range is -20 to +70. All of the quartz crystals, most of them, 99% of the ones that I've purchased were from ECS. I also purchased the crystal oscillators from ECS. And everything I purchased was 10 parts per million or better as far as tolerance goes. I spent the money for it. Might as well get the top tolerance we can get. So what I did was I put the crystal in my vector network analyzer, and I just did an S21 measurement, and lo and behold, there you go. These are called the overtones, I believe, and that's your fundamental. Okay, this is very, very, very narrow. This has a Q, a very intense Q, because it's a very narrow. There's no way you can confuse this with an RLC circuit. No way in heck. Okay, so this model here is not, it's just a very loose notional representation of this. There is no way that you can apply models to this to be able to come anywhere close to how this is behaving. And I'm sure this is what engineers do when they make the crystal oscillators, is they tune them in the field, and that's why they're able to get the precisions that we're looking for with the canned crystal oscillators. Okay, so we're going to return to more detailed VNA measurements later. Let's look at the way crystals are applied, okay, by all the devices that we talked about. All the devices use what's called a Pierce oscillator. Okay, developed by George W. Pierce, and this Wikipedia says the Pierce oscillator is a derivative of the Colpitts oscillator. Virtually all digital IC oscillators are of the Pierce type. Okay, and again, I go back to saying, well, this guy here is designed to drive high capacitance, so this capacitor shouldn't be doing anything. So I don't understand how they say that this is a derivative of the Colpitts oscillator. It makes no sense to me. And later on down the page, just if you scroll one page down from that Wikipedia article, they go, oh, this article needs attention from an expert in electronics. The specific problem is the description is confused about the operation of the circuit, and the diagrams do not show the crucial phase lag components or the need for the high gain amplifier. The crucial phase lag components is the way a Colpitts oscillator works. It uses the phase lag of the L and C components to achieve the Barkhausen criteria so the oscillator will work. Okay, and you need to get a total of 180 degrees phase shift through the crystal, but they're not seeing that. They don't understand how to do that because you're not going to get that with using the legacy model for the crystal. You're not going to see this. And this is the problem. This is what the problem I see everywhere, is people just do what they're told in college and they don't even think about this. Okay, so but I understand what happened. The Colpitts oscillator and the Pierce oscillator appear next to each other in the textbook. Okay, and I can see how somebody could confuse it. I don't know if Pierce did that, but I can see how because I don't know how Pierce derived the oscillator. I haven't seen the Pierce derivation of the oscillator. I haven't seen a derivation in any of the textbooks. None of the textbooks I have even do the derivation because I think it's gibberish. And I think a lot of the old textbooks, but they show it right next to. So if we look at a Colpitts oscillator, this is a Colpitts oscillator. Now just assume that this is a linear inverting amplifier, not necessarily a logic chip. Okay, this capacitor doesn't do much. All it does is a coupling capacitor that blocks the DC into this leg, which, you know, they have one in the Colpitts oscillator here for everybody else, but you don't really need that for here. You don't need it. You need it for the Hartley oscillator. You don't need it for the Colpitts oscillator. Okay, and so what happens is this guy, because he's an inverting amplifier, you get the 180 degrees here, because for the Barkhausen criteria, you need a complete phase delay around the loop of 360 degrees. Because this guy is an inverter, it's automatically 180 degree phase shift. Okay, and then you get your other phase lag by using this inductor and this capacitor. That gives you 45 degrees. And this inductor and capacitor gives you another 45 degrees. I think it's more than that. I think there's also a resistor here I might have forgotten. And between that, you get the phase lag, which makes the Colpitts oscillator work. Okay, now, but the cool thing is this coupling capacitor could actually be moved to this line over here, and it won't affect the operation. And then what we can do is say, well, gee, the inductor here has a resistance, and we can represent that resistance by another resistor out here. Okay, so right here you can see, if we bring up the model of the legacy model of the crystal, you can see that the components here in this band look like the components you get in the crystal, and I can see how they could confuse this with the Colpitts oscillator. Okay, this is the Pierce oscillator here. This is the Colpitts oscillator. You can see that if you replace the crystal with this, it looks like it should work just like a Colpitts oscillator. But again, this is not the representation of a crystal, and that's where the confusion is. So again, we have to achieve the Barkhausen criteria. not to be confused with the Barkhausen effect. In the Barkhausen criteria, again, we need to achieve 360-degree phase shift around the oscillator in order for this to oscillate. And again, we get 180 degrees just from the fact that this is an inverting amplifier. And because this is a logic chip, again, I'm saying this has absolutely nothing to do with this circuit, nothing to do whatsoever. And so it must be between this and this that you achieve the 180-degree phase shift. Okay, so now one thing I realized after I made the measurement before is that the PNA has only a 50 ohm load here, and that can actually load down the crystal. So what I've done is I put a 1 kilo ohm resistor in series to reduce the load of the VNA on the crystal circuit. And so the first thing I'm doing here is I'm calibrating the VNA. I've got this 22 picofarad capacitor unhooked, and what I'm doing is calibrating the VNA through the 1 kilo ohm resistor to take out the effects of the cables and the 1 kilo ohm resistor. Okay, then we're going to take all of our measurements by moving this to this one, which will allow us to go through the crystal and then through the resistor. And so we're going to measure once without the capacitor connected, and then we're going to measure with the capacitor connected to show you the difference of this capacitor. This is C1. We're not going to have any C2s here, none at all. I'll show you later on. We can put that back in and it won't make an effect at all on how the oscillator works. Okay, and that is our amplitude, our S21 amplitude, and again we're seeing this ridgy pattern here. The more important thing is the phase. Okay, with the phase, okay, our standard phase through this phase up here is about 70 degrees. This phase is going through the bulk capacitance of the crystal. So we got a plus 70 degree phase shift just going through the bulk capacitance of the crystal. And then where we get to the crystal, we're going from plus 70 to minus 90. So this is a minus 160 degree phase shift here. So now what we're going to do is now we're going to put the 22 picofarad load capacitance back on. Now this is going to shift everything down. It's going to go over off the bottom of the thing. So the next chart's going to look smaller. That's because I had to reduce the scale so it wouldn't go off the bottom of the screen. So now what you see is our capacitor canceled a lot of the effect of the bulk capacitance. And now we're up to about 30 degrees of phase bias here. And this guy goes down to about minus 140 or 150, somewhere around there. They may be going a little bit further because this is aliasing. So we got 150 and 30. So right there we have a 180 degree phase shift. Okay, so we're getting 180 degrees phase shift just with the crystal and the 22 picofarad load capacitor. We don't need anything else. So what we're going to do is we're going to hook up that circuit, the Pierce oscillator, using a 74AC04, and we're going to show you what we get with it. Okay, so here's a 74AC04. We're just going to we're going to change this capacitance from 10 picofarads to 47 picofarads, show you, what you get. We're not going to have a C2 over here, no C2 over here. And R1, we're going to use 47K. We use values up to 100K. It made no difference at all. We just need enough feedback to get this guy to start become unstable. That's all. That's the whole purpose of this, is to get this guy to become unstable so it'll start kicking into operation. Okay, and then what we're going to do is we're going to put the output of this into a divide by 16 ripple counter so that we can measure the frequency using an Agilent 6.5 digit multimeter. Okay, the reason why we have to divide by 16 is because the Agilent 6.5 digit multimeter cannot measure anything more than 800 kilohertz. So we have to downsample or divide the frequency down from 10 megahertz. This will end up being somewhere around 640 kilohertz in here, somewhere like that. Okay, and that's what we get. Okay, this is now this is a few little bit more because we measured the capacitances and we added in the input capacitance of the circuit. The 74AC04 has an input capacitance of 2 or 3 picofarads. So these values are a little bit off from the actual capacitor. Okay, 10 megahertz is what we're desiring, but we're going to show this in terms of error. This is our error from 10 megahertz. So this is 10 megahertz here. This is 500 hertz above, 1000 hertz above, 500 hertz below, 1000 hertz below. The red line here is, this is 10 parts per million. This is the rated precision of the crystal, and this is 50 parts per million. So if we were just to put in the load capacitance, load it with the load capacitance, we'd be around 50 parts per million error here. And if we were to put in the 36 picofarad as recommended in the data sheet, we'd be outside 50 parts per million here. So in any event, we could put a very wide variety of capacitors in here and still be within 100 parts per million. Okay, so we could be wicked off here, and this thing would still work to an accuracy of 100 parts per million, which is still fantastic. Okay, but okay, I want this precision here. I want this. If we can get this, I want this. Because if we can reduce any kind of error in any of our measurements, that leaves a lot of margin for identifying things that are not measurement error, but there's something else that might be remarkable. Okay, now what I did in the next one is I added in the C2. I put the C2 in and I made the measurements, and you can see the red line basically plots right on top of the other line. You can't see it in some case. I didn't take all the measurements, but I took enough of them. Now what's happening is this is causing a slight effect, because what it's doing is it's making it more difficult for this amplifier to pull the signal high. So it's actually causing a propagation delay in the order of nanoseconds. Okay, and so this is causing a slight frequency decrease, okay, because this red line is below the blue line due to propagation delay, but it has nothing to do with the theoretical operation of this oscillator. So this guy is completely not needed, especially since if you take this guy and you go and drive another chip with it, that chip may have input capacitance of up to 10 picofarads. So just by loading this, by driving other chips, you're going to end up with other straight capacitance on the end here, which are going to offset you a little bit anyway. But again, it's not going to be that critical as far as, you know, being a theoretical problem with the frequency you're trying to achieve. Okay, then what I did is I measured 18 crystals. I set it up where I put 22 picofarads on, and by including the 3 picofarads of the input capacitance, that gives us a total load capacitance of 25 picofarads. And then what I did is I measured 18 crystals. I just put one in right after the other and measured them, and all of these crystals came out within plus or minus 5 parts per million, which is fantastic, absolutely fantastic. So this shows unequivocally that this 10 part per million precision is achievable. What this orange line shows you is how much if you change the load capacitance where this line of crystals move. Each one of these nubs is 1 picofarad. So if I reduce the load capacitance by 1 picofarad, all these blue things are going to shift up by 5 parts per million. So 1 picofarad, we are moving this 5 parts per million. And that shows, so now I have some reference for, you know, how accurate do I need to be with the load capacitance to get my crystal within the designated range that I'm looking for. So now what I'm going to do is I'm going to show you that using a sine generator going into the crystal with just a 22 picofarad load, and show you the output on the scope, that the 22 picofarad capacitor is all you need to get the 180 degree phase shift. So here's the input signal. Okay, here's the output signal, and you notice they're 180 degrees out of phase with each other. If you take off the 22 picofarad capacitor, I actually have that down here. That's what you get. That's what you get with 10 megahertz without the 22 picofarad capacitor. Okay, and you notice you get a Q rise here. Okay, and so you're getting like 20 volts out. You're putting 4 volts in, you're getting 20 volts out. It's not over unity, it's just called Q rise. Okay. So the end of part 1, the conclusion is that the 10 parts per million accuracy is definitely achievable. And the age-old crystal equivalent model is notional at best, and people got to stop looking at that as gospel as far as how crystals operate. In part 2, I'm going to try to derive a more modern equivalent model for a crystal that you can actually use mathematics on. The old one's got to go. Okay, number 3, we found the Pierce crystal oscillator model is complete gibberish. It's not a Colpitts oscillator. I don't know where people get that. I don't know if Pierce actually developed it from that. But if he did, he did it because they used the legacy model for the crystal, which is garbage, and it does not explain how it works. You don't need 2 capacitors. We showed you with the previous slide that just with one load capacitor and the crystal, you can get your 180-degree phase shift out of that network right there. Okay, now what we did show, number 4, this should be number 4 here, is that if you follow the application notes in the data sheets, okay, you're going to get a pretty good result. It's going to be 100 parts per million at best. And you don't have to be that accurate with the crystal, with the capacitor. I would say for a lot of these devices that have the built-in capacitance, just use the built-in capacitance. If you're not looking for the precision I'm looking for, and don't bother adding any extra capacitance unless there's no built-in capacitance. Okay, but what it means for us is that in order to get that precision, we're going to have to tweak each one and have the ability to tune each one of them to get into that sweet spot of 10 parts per million. Now be careful, because some of the data sheets use the pin definitions backwards. Well, it depends what your reference is for backwards. So some extal in means extal into the crystal, and extal out means extal out from the crystal. And the other ones, extal in means it's the input to the crystal driver in the chip, and extal out is the output of the crystal driver of the chip. So in and out is ambiguous depending on which chip. So you got to be careful. If you're just going to use the single capacitor method that I'm explaining here, make sure you have it on the right pin. Okay, that's all I'm saying here. So in part 2, we're going to measure more crystals under different conditions to devise a more deterministic way to compute the needed value of C1, if that is indefinitely possible. I got a feeling that we're just going to come close. We're still going to have to put a means to tweak it, like a little variable capacitor that we're going to have to tweak it, but that's okay. As long as we know what we need in the range that we need, that's all I need in order to select a part to do that. And also we're going to try to reverse engineer the data that we've taken to develop a more deterministic crystal model. Okay, from my looking at it, it looks like the crystal works more like a waveguide, because when you apply a voltage across the crystal, you're causing a convulsion to run down the body of the crystal. And so you're basically causing like a wave to travel across the crystal. And the way it reflects off the other end to come back, so you get the Q rise, it actually looks like the way a wave reflects off a open end of a waveguide, or a short end, depending on which phenomena you use. Anyway, that's all for this part 1, and we'll have part 2 out in a little while. I may not come back to it after the new year because I do have to get some stuff done for other things for Ethereal University. Thank you very much. Oh, my Patreon folks are going to see this long before Ethereal University is out and published, because they get to see stuff first. Thank you.